Hello and welcome to this module. In the previous two modules, we saw applications of Fourier bases, circular matrices, very hands-on calculations involving circular matrices. You may be wondering where all this is coming from. Why is it that a circular matrix has an orthonormal uh, set of eigenvectors, right? So that might be interesting to you. We have seen before that self-adjoint operators or symmetric matrices have such properties, right? Symmetric matrices are characterized by that. They have real eigenvalues and they have an orthonormal basis of eigenvectors. So that's a very important characterization of symmetric matrices. Now circular matrices need not be symmetric. You'll see that they have a very different structure, but still they have a orthonormal set of eigenvectors, and that was very useful in signal processing. So what is the theoretical idea behind it? And that's where this notion of normal operators and matrices come through. Since it's sort of theoretical, I'm going to go through it a little bit faster, but for you to just know where this notion is coming from. It's not so critical for this course as such, but you'll see some of the ideas are very, very interesting. Okay. So if you generally think of any operator which will have an orthonormal basis of eigenvectors, how do we characterize it, right? So we saw that the circular matrices had that, symmetric matrices have that. So how do we think of generally operators with an orthonormal basis of eigenvectors? So let's begin with an operator T from say Cn to Cn, and let's say it has an orthonormal basis of eigenvectors, right? U1 to Un. We have an eigenvalue corresponding to uk, which is lambda k, which could be a complex number in general. Tuk is lambda k uk. Now, if the operator is self-adjoint, we know that this lambda k is real and the matrix ends up being symmetric or Hermitian symmetric, right? So, we say symmetric in the real notion, Hermitian symmetric in the complex notion. So, self-adjoint is very easy. It's a special case of this. It turns out self-adjoint is not the only case where you can have orthonormal basis of eigenvectors. So, here is a circulant example, right. So, 1, 2, 3, 3, 1, 2, 2, 3, 1. This matrix is not symmetric, but it has an orthonormal basis of eigenvectors. So, how do we study these kind of matrices? So the crucial difference between symmetric and this case is the eigenvalues of this matrix will not be all real. They will be complex. So, even though the eigenvalues are complex, you can have an orthonormal basis of eigenvectors, and that leads to the study of what are called normal operators. So, how do you characterize operators with orthonormal eigenvector basis? No matter whether the eigenvalue is real or complex, you go to this definition of an orthonormal, you go to a definition of a normal operator. Okay, so self-adjoint operators have this additional property that the eigenvalues are real. What if I only want the orthonormal basis of eigenvectors? I don't care about the eigenvalues real or not. So then self-adjoint is overkill, right? What is a little bit relaxation of self-adjoint? That is the normal condition. Okay, so let's see that. Okay, so these are definition of a normal operator. An operator T is said to be normal. Okay, the word normal, don't use the English definition of the word. The way to define it is normal. Okay, so it has one norm type behavior. We'll see that later. Okay, if T star equals T star T. Okay, so this is the definition of a normal operator. Contrast with the self-adjoint operator, right? What is self-adjoint? T equals T star. Okay, now in normal operator, T need not be equal to T star. You need not have that symmetry between the operator and its adjoint, but T times T star has to be the same as T star times T. So, T and T star have to commute. This is called commuting, right? If AB equals BA, we say that they commute. So, this operator has to commute with its adjoint. So, that is called a normal operator. Normal not meaning in the same as ordinary or something, normal, okay. Some norm related connection is there when you have this condition. So, in terms of matrices, if A is a matrix of T with respect to an orthonormal basis, okay. So, this orthonormal basis is important because only then we know that T star, right, if T is represented by A with respect to an orthonormal basis, T star is represented by A Hermitian with respect to the same basis. We know that. So, that is important to know. So, in terms of the matrices, T is normal if and only if A times A Hermitian equals A Hermitian times A. Okay, so that is the condition. Now, of course, symmetry you see is a very special case. A equals A Hermitian. Here you don't need that. You need these two products to be the same. Okay. So, if let us say operator is self-adjoint T equals T star, clearly T star equals T star T, right. So, it's T square. So, clearly A equals A Hermitian also gives you that A square equals A square. So, you get all these conditions satisfied. So, self-adjoint implies normal. If you have a self-adjoint operator, it is also normal. Okay. So, a lot of properties of self-adjoint operators will also generalize, but sometimes some properties will not be true. Okay. So, in normal we relax the constraint. It need not be self-adjoint, but it has to commute with the norm. So, the question that one may ask is, can there be a normal matrix that is not self-adjoint? If you do not have T equals T star, but it will still be normal. Yes, we have seen examples before. Here is a very simple example, A minus B, B A. If you do this, you will get, this is not equal to, it's adjoint, okay, A, B are all real, okay. So, this is not a symmetric matrix, so it is not self-adjoint, doesn't represent a self-adjoint operator, but it is normal. You can check that A times A transpose equals A transpose times A. In fact, it will be equal to A square plus B square on the diagonal and 0 on the off diagonal, okay. So, both are equal. So, this is normal. Also, the circulant matrix that I had, you can check this. This also will commute with its transpose. So, this is A transpose will be equal to A transpose A. You can check that. So, there are matrices which represent normal operators, but they don't they are not symmetric, okay. So, that this is an interesting set, it is a more general set than before, okay. So, what is this normal operator? So, there is a norm connection I was mentioning, so that is where the definition comes from. It turns out if T is normal, norm of TV and norm of T star V are the same. The operator and its adjoint, can be very different. There's one is represented by the transpose of the other, but if T is normal, then if you do TV and you just twist around T star and still you multiply by the same V, the norm has to be the same, okay. So, that is where the definition of this normal comes from. The proof is actually, I am going to go through it very fast. Proof is not important for us, but this property is very important, okay. Try to remember this property, operator and the adjoint will take a vector to places so that the norm is always the same, okay. So, that is where the name normal comes from. Proof, let me go through very quickly. If you look at norm TV square is TV comma TV in a product. Now, use the property of the adjoint to push this T to this side. Now, use the normal property here, right. T star T is the same as T T star, okay. Here is where I am using the normal property. Now again use that adjoint property, bring this T to this side, you will get T star here. So, T star V comma T star V, and that is norm T star V squared, okay. So, you see that this is true for any normal operator. So, it means it is also true for a self-adjoint operator, obviously, right. T equals T star, norm TV is norm TV, right. So, both of them are the same if they are self-adjoint, but for normal also it is true, okay. So, in fact, there is a curious property that the converse of this is also true. Supposing an operator satisfies this for all V, then it is normal, that T star equals T star. I am not proving it here, but you can prove that, okay. Here is the next property that is very interesting. So, eigenvector of a normal operator and its adjoint, okay. So, supposing you have an eigenvector for a normal operator with eigenvalue T, okay. So, here is a curious property about eigenvectors. So, this is also a very important crucial property. It turns out T and T star, even though they may not be the same, but if T is normal, then there is a strong connection between eigenvectors of T and eigenvectors of T star. Of course, if it's self-adjoint, T and T star have the same eigenvectors, no big deal in saying that. But in general, what do we know about T and T star? If T has an eigenvalue lambda, T star has an eigenvalue lambda bar. We know that that's also true, right? T and T star have the same eigenvalues, but eigenvectors are a bit complicated, right? T is I mean, think of it in matrices. You have a matrix here, M times V. So, if you do the adjoint here, you're not adjoint. If you do the transpose here, you're getting M transpose M Hermitian. If I multiply by the same V, I may get something else, right? I mean, it's not clear because you've done the transpose operation. It's not clear that M times V and M Hermitian times V will have to give you something similar, okay. But if it is normal, if the matrix is normal, then the two things are connected, okay. So, that's why this normality becomes a strong constraint. So, V is an eigenvector of a normal operator T with eigenvalue lambda, then V is also an eigenvector of T star with eigenvalue lambda bar, okay. So, that's the connection. So, I know T has eigenvalue lambda, T star will have an eigenvalue lambda bar, but the eigenvectors of these two are the same when T is normal, okay. So, it's very strong connection, and the proof goes through quite easily. It's a little bit involved, but maybe you can see it very quickly. If T is normal, then T minus lambda I is also normal, okay. So, the proof is not too bad. T minus lambda I star we know is T star minus lambda bar I. So, now just with this you can multiply T minus lambda I times T star minus lambda bar I is T star. This is just matrix algebra, right. But now you notice you can do this switch. T star is the same as T star T, okay, and then do this switch, okay. Everything else remains the same here, and now you can see that this is also the same as this guy, T star minus lambda bar I times T minus T. Because we could do the switch, T star is T star T, these two become equal, okay. So, for normal operators, when you do T is normal, T minus lambda I is also normal, okay. So, once T minus lambda I is normal, use the norm property, right. What is the norm property? norm of t minus lambda iv is the same as norm of t star minus lambda bar iv. Okay, t and a normal operator and its Hermitian conjugate, right, and its star have the same norm, right. So when you multiply with the vector v, t and t star, if t is normal, t and t star have the same, the operator and its adjoint have the same norm when any melter multiplies it. Now we know t minus lambda I is also normal, so you apply the property, normal property to t minus lambda I. So t minus lambda I v norm has to be equal to t star minus lambda bar I v norm for any v. Okay, so now v is an eigenvector, which means for t, which means norm of t minus lambda I v is 0. So this also has to be 0. So v has to be the eigenvector for t star as well. Okay, so that's a very powerful property. Now that property and the norm, that property of eigenvector being the same for t and t star, but giving you the lambda and lambda bar, is enough to show this powerful property that v1, v2 are eigenvectors of a normal operator corresponding to distinct eigenvalues. Then v1 and v2 are indeed orthogonal. Now this is a property that you have for self-adjoint, right? For self-adjoint you have this, right? Absolutely, you have this property. Distinct eigenvalues for a self-adjoint operator, symmetric matrix for instance, correspond to orthogonal eigenvectors. Same thing is true for normal operators as well. So here is a quick proof. Lambda 1, lambda 2, or let's say the corresponding eigenvalues of v1, v2. v1 has eigenvalue lambda 1, v2 has eigenvalue lambda 2. Lambda 1 and lambda 2 are not equal, right? That we know. So you just start with this kind of an inequality, right? So t v1 comma v2 is v1 comma t star v2. So this is just the definition of adjoint, right? Adjoint has this definition. On the left side you will get lambda 1 v2, because you know v1 is a eigenvector of t with eigenvalue lambda 1. Lambda 1 will come out, you will get this. Now t star v2 is also an eigenvalue of t star. What is the v2 is also an eigenvector of t star, and the eigenvalue is lambda 2. v2 is an eigenvector of t star with eigenvalue lambda 2 bar, right, the conjugate of lambda 2. Okay, so we are going to use that property here and we will write it as lambda 2 bar v2. Now lambda 2 bar v2, when I multiply on this side, is going to come out as lambda 2, right, because that is the second argument of an inner product. It's going to come out as lambda 2. So lambda 1 v1 v2 is lambda 2 v1 v2. Bring this to this side, lambda 1 minus lambda 2 and v1 v2 is 0, and that's done. Okay, lambda 1 is not equal to lambda 2, so v1 v2 has to be 0, v1 v2 are orthogonal. Okay, very nice simple proof. Okay, this property is similar to that for self-adjoint. Notice that you don't need self-adjoint for this orthogonality property. Normality is enough. Okay, so that's important. Okay. Here is the final thing. So now we know that any two eigenvectors are orthonormal for a normal operator, orthogonal for a normal operator. The final thing we have to show is there will be no multiplicity issue, right? So in self-adjoint also we had to show that there will be a full set of eigenvectors. Like that for normal operators also we have to show that there is a full set of eigenvectors. There is no multiplicity issue. If you have algebraic multiplicity, the geometric multiplicity is equal to algebraic multiplicity. If you remember the proof in the self-adjoint case, we used the upper triangularization and we showed the upper triangularization in the symmetry case will actually be diagonal. Same thing we are going to prove here. Okay, so any operator T is upper triangular with respect to an orthonormal basis. We know that. Let's say you have a normal operator T, and let's say A is the upper triangular matrix which represents T with respect to an orthonormal basis u1 to un. Okay, so I'm going to skip through this proof, not do it in full detail. So if you have A being a matrix for T, A Hermitian is a matrix for T star with respect to the same basis. Now you start equating in this upper triangular matrix A norm T ui squared and norm T star ui squared. Okay, remember if A is upper triangular, A Hermitian will become lower triangular. Okay, so T times ui, right, with respect to A is only like upper triangular, right, only one value, everything else is 0. But T star ui is A Hermitian, so it will have it could have a lot of values, but both have to have the same norm. So if you equate the two norms, you can show A is diagonal. Okay, so this step I am skipping. It's actually not too hard, but you can see it. Okay, so the converse also we'll skip. Its converse is actually very simple, but still we'll skip that. Okay, so basically what we have shown is all the proofs that we need. Any normal operator T star equals T star T, or in matrix terms A Hermitian equals A Hermitian A. If you have a matrix satisfying that, then it has a full set of orthonormal eigenvectors. So you can do an orthonormal decomposition. So let's look at the decomposition for the normal matrices. I'll quickly close with these simple things. Okay, so if you have an A being an n by n normal matrix, there are n eigenvalues. These could be complex, these could be repeated, doesn't matter. And you also have n orthonormal basis of eigenvectors, a u, a is lambda, a u. Okay, so it turns out you can do this orthonormal decomposition. Any normal matrix can be written as lambda 1 u1 u1 Hermitian plus so on till lambda n un un Hermitian. Remember, u1 un Hermitian is a rank 1 matrix, right? Rank 1 matrix. u1 is a column vector, u1 Hermitian is a row vector. Column vector times row vector is a rank 1 matrix, right? So you have a bunch of rank 1 matrices, scale them by the appropriate lambda that you want, you add them up, you get a normal matrix. This is like if and only if. Any normal matrix can be written like this. Any matrix that you write like this is also normal. Okay, so that's how it works. You have to start with the orthonormal basis. You can always write like this. But the crucial part is the lambda I here can be complex. In the normal case, it can be complex. If A ends up being symmetric or Hermitian symmetric in the complex case, then the lambdas will be real. If you put lambda real values here, you get Hermitian symmetric matrix. If you put lambda complex values here, you get a normal matrix. Okay, very simple description for normal matrix and symmetric matrices. These are called complex spectral theorem. This is called the complex spectral theorem. Okay, so the proof is actually very easy. You just take the orthonormal matrix decomposition, write like this, use the matrix of definition of inner product, you will get this. Okay, so that's the thing about normal matrices. Okay, so a couple of quick proofs here. First is circular matrices are normal. Okay, so we saw that circular matrices need not be symmetric, but they are normal. So how do you prove it? M is like this, M Hermitian is like this. Okay, so you just go through it, columns become row, and then you do the conjugations, and then you have to look at the product. Okay, so let's look at M Hermitian and M Hermitian M. Okay, let's look at the I comma ith term. I comma ith term is first row multiplied by the first column, right? First row multiplied by the first column, or second row multiplied by the second column, or third row multiplied by the third column. If you do any of these products, you will see that the I comma ith row is always ith entry of M Hermitian, M times M Hermitian is always of this form: h0 bar plus hi bar plus hn minus 1 hn. You can check this. You take the first one, multiply, you get the same expression, right? Second row multiplied by the second column, you get the same expression. So I comma ith term is the same. Curiously, the other one is also the same. I'll leave you to check this. You take, the ith row of first row of this guy, M Hermitian, multiply by the first column here, you get the exact same expression. Okay, you can check that this have to be true. Okay, I comma I is the same. You can also do I comma I plus 1. First row multiply by the second column. First row here multiply by the second column here. You will see that the expression is exactly the same. You get this h0 h1 bar, hi plus 1 bar, hn minus 1. Of course, there's no hn. Hn is the same as h0, so it becomes h0 bar. Both of these are exactly the same. So you can push this to I comma I plus j. Of course, I can do I plus j. I have to do modulo n, as in I have to take the remainder when I divide by n. So that I will denote as the square braces n. Okay. So if you do that, you will see that this expression and this expression are the same. I'm not going to go into detail. You can check that this will also be exactly the same. So circular matrices are normal, and no wonder they have a unitary, they have a orthonormal basis of eigenvectors, and curiously enough, for circular matrices, the Fourier basis ends up being that basis. Okay. Another very interesting property is that the unitary operators, matrices that are unitary, they are also normal. Okay, so that's like a curious relationship. So if you take a unitary operator T, let's say, is represented by a matrix A with respect to an orthonormal basis, of course. So T star is T star T is I, and A Hermitian A is equal to I. Okay, so clearly unitary implies normal. T star is T star T, but in fact for unitary case, both have to be equal to the identity operator. It's a stronger constraint than normal. Unitary implies normal. Normal doesn't imply unitary. What else do you need? You need the eigenvalue property. What is the eigenvalue property? If T is unitary and lambda is an eigenvalue of T, then it turns out absolute value of lambda is 1. Okay, so here is an interesting property. For any unitary matrix, the absolute value of an eigenvalue will be equal to 1. Proof is actually very easy. Here is the proof. Let's say V is an eigenvector of T with eigenvalue lambda. Now T is also normal, right? So T star, the same vector V will be an eigenvector for T star with eigenvalue lambda bar. Okay, that also we know. So TV is lambda V. You multiply both sides by T star, right? So T star TV is lambda T star V. Now T star TV is V, right? Because T star T is I. I'm using the unitary property here. T star T is I. Now T star V, because of this eigenvector property, is lambda bar V, and that means lambda bar is equal to 1. Okay. Now this actually is the converse, So if you have a normal matrix, all of whose eigenvalues have absolute value equal to 1, then it is actually unitary. Okay, so that's also a very powerful connection. Okay, so with that we'll close this module. The last module was a little bit more theoretical, putting the normal matrices in a clear framework that we studied before. Okay, thank you very much.